Hello students, I welcome all of you. Today our lecture is about the structural elucidation techniques of alkaloids. Before going into the actual lecture session, I had a few words of advice. You should be familiar with the basic functional group chemistry such as the identification of alcohols, aldehydes, ketones and amines, etc. And the second thing is that you should know the strategy of identification of organic compounds that you learned in the BS second semester of the chemistry course. So I believe that you know how to detect the different elements such as nitrogen, sulfur and halogen among the organic compounds, in addition to the knowledge of the strategy of the detection of the different functional group in the organic compounds. So these two things will help you a lot for the structure elucidation of the alkaloids. As I have already informed you, for the structure elucidation of alkaloid, you should have a basic chemistry knowledge about the detection and the conformation of different functional groups in organic compounds, in addition to the detection of the nitrogen, halogen and sulfurs. You should also be familiar with the different physical techniques like filtration, solubility test, flame test. If you are equipped with this knowledge, the structure elucidation of alkaloids will be very easy task for you. The strategy for the structure elucidation of alkaloids is almost the same as used for the structure elucidation of the organic compounds. First of all, we will study the physical and the chemical properties of the unknown alkaloids or the organic compounds. Then we will go for the presence of the or the absence of the different functional groups by chemical testing, such as for the presence of alcoholic group, for the presence of aldehyde or keto groups, and we will go then for the elemental analysis. Elemental analysis will let you know the empirical formula of the alkaloid, unknown alkaloid. Molecular weight determination is followed by mass spectrometry. Mass spectroscopic analysis will give you the exact molecular weight of the unknown alkaloid. Then you will go for the proton and NMR studies for the structural elucidations of the hydrogen atoms. It will tell you to which carbon or in what manner the hydrogens are present in the alkaloid. Then you will go for the carbon 13 NMR to determine the carbon skeleton of the alkaloid. If the unknown alkaloid is crystalline, then you will go for the single crystal XRD, which will give you the exact three-dimensional structural formula of the alkaloid or any other organic compound. In the old days, synthesis of the organic compound was performed as the final step for the structural elucidation of the unknown alkaloids, but this technique is still a gold standard for the final confirmation of the structure of any of the organic compound. So if your organic compound is crystalline, you may go directly for the single crystal XRD. If it is amorphous, then you may go for the elemental analysis followed by the proton and carbon 13 NMR studies. So this is the sequence that you will follow for the structural elucidation of any of the alkaloids. So the first step in the structural elucidation of alkaloids is the study of its physicochemical properties. In physicochemical studies, we will find the color, melting point, boiling point, and the physical appearance of the alkaloid, either it is crystalline, amorphous, etc. These physical properties help us a lot. For example, caffeine is crystalline solid. On the other hand, amethine is an amorphous solid. Nicotine and quinine are volatile liquids. Pilocarpine and hyoscine are the non-volatile liquids. The other physical chemical property is the color of the alkaloid. Majority of the alkaloids are colorless. However, some are colored. For example, colchicine and berberine are yellow in color. So sometimes just the color of the alkaloid inform you about the structure of the alkaloid. Solubility is another very important physicochemical property of alkalides, since majority of alkalides possess nitrogen hydrocycle and these are basic in their nature. Generally, alkalides bases are lipophilic and their salts with hydrochloric acid and sulfuric acid are hydrophilic. Exception to this rules includes the water-soluble alkalides caffeine, ephedrine, codeine, colchicine, pilocarpine, and quaternary ammonium alkalides. Some alkalides naturally exist as quaternary ammonium salts, so they get dissolved in water. Whereas the majority of the free alkalides are lipophilic and do not dissolve in the water, whereas their salts with hydrochloric acid and sulfuric acid get dissolved in water. For example, aniline is insoluble in water, whereas its salt with hydrochloric acid. When it is made to react with 0.1 normal hydrochloric acid solution, it gets dissolved in water, and it upon reaction with sodium hydroxide again precipitate in water. So same is true for the majority of the alkalides. To this exception, there are some water soluble alkalides like caffeine, ephedrine, codeine, colchicine, pilocarpine, and quaternary ammonium alkalides. Some alkalides are soluble in organic solvents. Examples to these alkalides include morphine dissolved in ether, theobromine and theophylline dissolved in benzene. Sometimes salts of the alkalides are insoluble in water. For example, quinine monosulfate is not fairly soluble in water. It gets dissolved in water, but it is not fairly soluble in water. Chloride salts of lobeline and atropines are soluble in chloroform. So when you are checking the solubility of an alkali, you must be very careful. This anonymous behavior of the alkalides is because of the presence of many different types of functional groups in the alkaloid structures, which give the properties of the solubility towards a particular solvent to the alkaloid. So you should be careful. If some alkaloid is soluble in water, then you should not be affirmed, still confirmed with the presence of the some hydrophilic functional group. Because of the absence of the some hydrophilic functional group, some alkaloids still get dissolved in water. Among the three preliminary tests for the detection of alkalides, Dragon-Drop test is the most important test. If all these three tests which we are going to discuss one by one are the color test for the detection of alkalides. Dragon-Drop test was formulated by a German pharmacologist John George Dragon-Drop. Dragon-Drop's reagent is a color reagent to detect the alkalides in a test sample. Upon reacting with the alkalides, Dragon-Drop reagent produces orange-red precipitates, or sometimes it may also produce the orange-colored precipitates. If we talk about the composition of the Dragon-Drop reagent, it is a solution of potassium bismuth iodide prepared by the reaction of the bismuth nitrate and the potassium iodide. If you can prepare this reagent in your laboratory by adding the 1.7 gram of the bismuth nitrate in 20 ml of the glacial acetic acid, and then add 20 ml of the 80 ml of 50% solution of potassium iodide. Mix these reagents very well and make the volume up to 100 ml with the distilled water. This will be your stock solution. Take out the 10 ml of this stock solution and add 20 ml of glacial acetic acid and make the volume up to 100 ml with distilled water. It will be your working solution. Now add this working solution to your test sample. If the color of the test sample upon heating or at the room temperature turns to the orange-red precipitates, or it turns to orange-red, then alkalides are present in your test sample, or otherwise it is negative with respect to the presence of the alkalides. Second most widely used color method for the detection of alkalides among the natural products is the Wagner test. Wagner reagent produces a reddish brown precipitates if the alkalides are present in the test sample. If we talk about its composition, it is an aqueous solution of iodine. As we know that the iodine is insoluble in water. So, and its triiodide anion is soluble in water. To convert the iodine into a triiodide anion, you have to add potassium iodide. So, add 2.5 gram of solid iodine in 12.5 gram of potassium iodide followed by the addition of 250 ml of distilled water produce the Wagner's reagent. The third most widely used chemical test for the detection of alkalides in the natural products is the Mars reagent. Mars reagent is a colored method used for the detection of alkalides in the natural products. Mars reagent is freshly prepared by dissolving a mixture of mercury chloride. Mercury chloride should be in 1.36 grams and potassium iodide 5 gram of potassium iodide. Then add 100 ml of distilled water. Shake the reagents thoroughly. Most alkalides are precipitated from the neutral or slightly acidic solutions of Mars reagent to give a creamy colored precipitate. So, if the natural product contains the alkalides, it reacts with the Mars reagent and produces a creamy colored precipitate. This test was invented by German chemist Julius Robert Braun, born in 1814 and died in 1878. The three less commonly used chemical tests for the detection of the alkalides include Hager's test, tannic acid test, and test by picrolonic acid. Hager test. Hager's reagent produce yellow colored precipitate from reacting with the alkalides. If we talk about its composition, Hager's reagent is a saturated solution of picric acid. So picric acid forms salts with alkalides since alkalides are basic in nature. Alkalides give yellow colored precipitate upon reacting with the Hager's reagent. The other less commonly reagent used for the detection of alkalides is the tannic acid. Alkalides give buff colored precipitate with 10% of the tannic acid solution. Picrolonic acid may also be used for the detection of alkalides. Alkalides produce yellow colored precipitates upon reacting with picrolonic acid. Like the other chemical tests, there are some chemical tests used for the detection of specific types of an alkaloid. So these chemical tests cannot be used for the detection of all the alkaloids. For example, Norexide test, it is used for the detection of caffeine. It is a mixture of potassium chlorate and hydrochloric acid in ammonia solution. It produces purple color if the caffeine is present. Similarly, morphine produced orange-red color upon reacting with dilute nitric acid. This test is used at the Air Force to screen the presence of the morphines. The suspect sample is dissolved in the dilute nitric acid. If it produces orange-red color, the morphine is suspected. The confirmation is made with the gas chromatography coupled with mass spectrometry. Alkaloids from the plant sample or animal samples are separated through the thin layer chromatography. Once they are separated on the thin layer chromatogram, their detection on the thin layer chromatogram is necessary. For this purpose, the thin layer chromatogram is separated with a reagent that that react with the alkaloid and give a specific color. These reagents can be used for the detection of alkaloids on the chromatogram, on the thin layer chromatogram. The one is called the Adam-Cavies reagent. It consists of a mixture of formaldehyde and hydrochloric acid. You may also use the Morpheus reagent. It is a mixture of formaldehyde and concentrated sulfuric acid. Macles and Mill region can also be used for the detection of alkaloids on thin layer chromatogram. It is a mixture of orthothaldehyde and hydrochloric acid. Range lowest region is another region used for the detection of alkaloid on thin layer chromatogram. It consists of a mixture of para-dimethyl aminocinnamaldehyde and hydrochloric acid. One earth region is another region used for the detection of alkaloids. It consists of a mixture of para-dimethyl aminobenzaldehyde along with an oxidant and concentrated sulfuric acid. Salmon region consists of sodium nitroprusside and acetaldehyde and sodium carbonate. Liberman region is the mixture of potassium nitrate and sulfuric acid. Macles region is a mixture of selenious acid and concentrated sulfuric acid. So you may note that all these regions used for the detection of alkaloids on the thin layer chromatogram is a mixture of an aldehyde and acid. Sometimes an oxidant may also be added. For example, in the case of one earth region, we have an aldehyde and an acid along with an oxidant. So you may use one of these regions for the detection of the isolated alkaloid on thin layer chromatogram. Once you have proved the alkaloid from the biological source through TLC analysis and you have also located the spot of the alkaloid, your next target will be the determination of its molecular formula and the molecular structure. The first step will be the elemental analysis. With the help of carbon, hydrogen and nitrogen analyzer, one can easily determine the percentages of carbon, hydrogen, nitrogen and sulfur present in the given pure sample of unknown alkaloid or organic compound. With the help of the percentages of the carbon, hydrogen, nitrogen and sulfur, an empirical formula is established. With the help of mass spectrometry, one can easily find the molecular weight of the given alkaloid. Once the molecular weight is established, one can easily find the degree of unsaturation of the alkaloid by the formula. This formula is given on the slide number 12. It is degree of unsaturation is equal to 1 plus half summation of Vi. Vi is the number of atoms with valency Vi. That is an atom that has a valence of X contribution, a total of X minus 2 to the degree of unsaturation. The result is then halved and increased by 1. So in this way you can determine the degree of unsaturation present in the given unknown structure of an alkaloid. Once you have determined the degree of unsaturation of the alkaloid, you may now assign it to a class such as it is an alkene or alkane. For example, if it contains one double bond, then it may be an aldehyde or a ketone, or if it contains a triple bond, then it may contain a carbon-carbon triple bond, and so on. How the functional groups are detected in the alkaloids. Here we are discussing this question. Since alkaloids are the natural product, so these may possess any kind of the functional group. So there is no limitation for the functional groups, and also there is no limitation on the number of the functional groups present in an alkaloid. An alkaloid may possess one or more than one functional group. Majority of the alkaloids may possess falling oxygen based functional groups. Oxygen atom may be present in many forms, like it may be present in the form of a phenolic hydroxyl group, or it may be present in the form of a alcoholic hydroxyl group. It may be present in the form of a methoxy functional group, or it may be present in the form of a acetoxy functional group. Benzoxyl is another functional group in which the oxygen is present. Oxygen may also be present in an alkaloid in the form of carboxylic group or in the form of carboxylate functional group. Carbonyl and lactone rings are the other representative functional group of oxygen. The other most important element present in the alkaloid is the nitrogen. Nitrogen may be present in the form of a primary, secondary or tertiary amine or as an amide. Since majority of the alkaloids possess large structures, for the determination of their structural frameworks, it is very useful strategy to break a part of unknown alkaloids and determine its nature by part-wise analysis. It means that once you break a part from an alkaloid and analyze it, then again break down the remaining part and keep on breaking, and at the end you combine all these parts to give the one large structure of an alkaloid. Different types of the strategies used to investigate the structural frameworks are include Hoffman exhaustive methylation and degradation method, von Braun method, reductive degradation and zinc distillation, alkali fusion and oxidative and dehydrogenation. These methods are particularly used for the degradation of the alkaloid structure from the nitrogen. One may also use the other oxidative degradation method. For example, you may use the ozone or the ozonolysis, and ozone adds to the unsaturated positions and break down the carbon-carbon unsaturated bonds. So one may use the ozonolysis for the oxidative degradation of alkaloids. Second most widely used color method for the detection of alkaloids among the natural products is the Wagner test. Wagner reagent produces a reddish brown precipitates if the alkaloids are present in the test sample. If we talk about its composition, it is an aqueous solution of iodine. As we know that the iodine is insoluble in water. So, and its triiodide anion is soluble in water. To convert the iodine into a triiodide anion, you have to add potassium iodide. So, add 2.5 gram of solid iodine in 12.5 gram of potassium iodide, followed by the addition of 250 ml of distilled water, produce the Wagner's reagent. The third most widely used chemical test for the detection of alkaloids in the natural products is the Mars reagent. Mars reagent is a colored method used for the detection of alkaloids in the natural products. Mars reagent is freshly prepared by dissolving a mixture of mercuric chloride. Mercuric chloride should be in 1.36 grams and potassium iodide 5 gram of potassium iodide. Then add 100 ml of distilled water. Shake the reagents thoroughly. Most alkaloids are precipitated from the neutral or slightly acidic solutions of Mars reagent to give a creamy colored precipitate. So, if the natural product contains the alkaloids, AMS degradation or elimination, also called AMS reaction or AMS reduction, is a method for the reduction of quaternary ammonium cation to a tertiary amine with sodium amalgam. For example, here in this slide you may see the reduction of a quaternary ammonium salt with sodium amalgam. Amalgam means for mercury. Amalgam always stands for the mercury. This organic reaction was first described in 1909 by the German chemist Hoffmann and was for a long time of great importance in the structural elucidation of many of alkaloids. For example, the structure of the ephedrine was elucidated with this AMS degradation method. Alternate reducing agent instead of sodium amalgam is lithium aluminum hydride. So if an alkaloid contain a quaternary ammonium salt, then upon reduction or AMS degradation, it produces a tertiary amine. In the previous slide, we have noticed that if an alkaloid contains a quaternary ammonium functional group, then we may use the lithium aluminum hydride or sodium amalgam, which react with this quaternary ammonium salt. If an alkaloid contains a tertiary amine, what degradation method will be used? For Under such circumstances, Braun degradation method can be used. The Braun reaction is a reaction in which a tertiary amine reacts with cyanogen bromide to give an organocyanamide. For example, when N,N-dimethyl alpha-naphthalamine is made to react with cyanobromide, a cyano-substituted secondary amine is produced. If we talk about the mechanism of this reaction, the mechanism of this reaction consists of two nucleophilic substitution steps. In the first step, the amine is the first nucleophile displacing the bromine atom, which then acts as the second nucleophile. In the coming slide, you will see another example with the detailed mechanism. Here you may see that the lone pair of the nitrogen of the tertiary amine attacks on the cyanobromide, leaving the bromide and thus producing a quaternary ammonium salt of bromide. Then this quaternary ammonium salt of bromine decompose, leaving behind a cyano-substituted secondary amine. It is a second order nucleophilic substitution reaction. In the previous slides, we have studied the von Braun's reaction. Don't confuse with the von Braun reaction and von Braun degradation method. The von Braun amide degradation is the chemical reaction of monosubstituted amide with the phosphorus pentachloride or thionyl chloride to give a nitrile or an organohalide. It is named after Julius Jacob von Braun, who first reported this reaction. Here in this example, you may see that an amide upon reacting with the phosphorus pentachloride is decomposed into a monosubstituted amide along with a alkyl halide. So, if an alkaloid contains an amide group, the von Braun degradation method can be used and the liberated alkyl halide can be analyzed. Let us now discuss the detection of the different functional group in the unknown alkaloid. For the detection of hydroxyl functional group, one may use the one of the following chemical test. The hydroxyl group, upon reacting with the acetic anhydride or acetyl chloride, will produce an ester, and ester are mostly of fruity smell. So if you want to know whether your alkaloid contains a hydroxyl group or not, you add a simple small quantity of acetic anhydride or acetyl chloride. And if you are interested in the quantitative and the qualitative test regarding the detection of the hydroxyl group, add the measured excess quantity of the acetic anhydride or acetyl chloride, and upon reaction now titrate the remaining acetyl chloride or acetic anhydride with a standard solution. So by this way, you may know how many hydroxyl groups were present. But the problem is that in addition to the hydroxyl group, there are many other active hydrogen containing functional groups that may also react with the acetyl chloride or acetic anhydride. Among these are the primary amines. Primary amines also react with the acetic anhydride and acetyl chloride and produce the amide. What strategy you will use to overcome this problem? I will inform you in the coming slide, but here it is a question for you, that you try to solve this question, that what strategy can be used to overcome that the acetic anhydride and acetyl chloride both react with an amine to produce the amide. Once you have determined that the hydroxyl group is present in your sample of alkaloid, you may further be interested to know whether it is alcoholic or phenolic. That is the second question that I am leaving for you, that how you will detect that the present hydroxyl group or the groups in your sample are alcoholic or phenolic. The answer to these two questions are very simple, very simple. So I will inform you in the coming slide, but here you have to think. Once you have detected hydroxyl group in your unknown alkali, now you are interested to know whether this hydroxyl functional group is phenolic or non-phenolic. For the detection of phenolic hydroxyl group, add 1 to 2 drops of neutral ferric chloride solution into the test solution of alkali. If the color of the test solution turns purple, it indicates the presence of phenolic hydroxyl group, or otherwise it contains non-aromatic hydroxyl group. If phenolic hydroxyl group is present, it will be soluble in sodium hydroxide solution and will reprecipitate out by bubbling the above solution with carbon dioxide. Once you have determined that either your hydroxyl group is phenolic or non-aromatic, next step will be the quantitative determination of the hydroxyl groups. The method that is used for the determination of total number of active replaceable hydrogens is called the Shogev-Garinov test. It is actually a Grignard reagent. When Grignard reagent is made to react with replace with the alkaloid, the hydrogen, the active hydrogens are replaced, and if your Grignard reagent is a methyl magnesium iodide, then methane gas will be liberated. From the liberated methane gas, the analysis of this liberated methane gas will inform you how many replaceable hydrogens were present in your alkaloid. But again, here the problem is that both hydroxyl amines and acetylenic hydrogens all react with the Grignard reagent, and here again we are confusing the hydroxyl groups with the amines and acetylenic hydrogens. Now we will use the specific test for the alcohols to determine how many hydroxyl groups are present. For the detection of alcoholic hydroxyl groups only, one may use the cetic ammonium nitrate solution. It, upon addition into the alkaloid solution, give a pink or red color, will indicate the presence of alcoholic hydroxyl group. So if the your sample contains alcoholic hydroxyl groups, it, upon addition into the cetic ammonium nitrate, will produce the pink or red color precipitate. What is the distinction between the primary, secondary and tertiary alcohol? Let us discuss some chemical reactions that can be used for the distinction between the primary, secondary and tertiary alcohols. One of them is the low-cost test. It is a mixture of zinc chloride and concentrated hydrochloric acid. It reacts with primary, secondary and tertiary alcohols at different rates. Low-cost reagents forms a cloudiness on reacting with alcohols. With tertiary alcohols, low-cost reagent reacts immediately and give cloudiness. Upon reacting with secondary alcohols, it reacts slowly as compared to the tertiary alcohols and give cloudiness after 5 to 10 minutes. And there is no reaction with primary alcohols. So low-cost test reacts with the tertiary and with the secondary alcohols, and it do not react with the primary alcohols. So with the tertiary alcohols, it reacts immediately and it produces the cloudiness, and with the secondary alcohols, it reacts slowly and it produces cloudiness after 5 to 10 minutes of addition. So if your alkaloid contains the alcoholic hydroxyl groups, which are primary or secondary, it will produce the cloudiness. Here is another test that is most commonly used, that is called the iodoform test. This test is given by the secondary alcohols, ketones and acetaldehyde. First, the compound is heated with sodium hydroxide and iodine. The formation of yellow precipitates of iodoform shows the presence of secondary alcohol or ketone. For example, here you may see that 2-hydroxypropane is heated with propanol. 2-hydroxypropanol is heated with iodine and sodium hydroxide. It first forms the acetone, which upon reacting with the iodine and sodium hydroxide gives the iodoform and sodium acetate. Note that the formation of yellow precipitates shows the presence of alcohol, which is a secondary alcohol, and acetaldehyde or methyl ketone. Jones reagent is used for the detection of primary, secondary, and tertiary alcohols. It reacts with the primary and secondary alcohols to produce aldehydes and ketones respectively. Jones reagent is a mixture of chromic acid and sulfuric acid. For the preparation of the Jones reagent, dissolve 10 mg or 2 drops of the unknown alkaloid sample in 1 ml of pure acetone, followed by the addition of 1 drop of Jones reagent. Remember that the Jones reagent produces orange yellow reagent, is an orange yellow color reagent. So if a positive test is brought by the formation of a green color within 15 seconds upon addition of the orange yellow reagent to a primary or secondary alcohol. So it reacts only with the primary or secondary alcohols. If your sample contain primary or secondary hydroxyl groups, then upon adding the Jones reagent, it will produce the green color within 15 seconds of the addition, after the addition. Some other reagents which give the false positive test includes the enols. Enol gives the false positive test. Phenols give a dark colored solution which is not blue green like a positive test. So you must have to take care of the false positive test also. A preliminary test for detection of carboxylic groups in your alkaloid sample is the litmus paper test. Dip a litmus paper into the aqueous solution of alkaloid sample. If it turns red, it indicates the presence of carboxylic functional group. A negative litmus paper test does not mean the absence of carboxylic functional group. Because of the presence of the nitrogens in the alkaloids, a litmus paper test may be negative even with the presence of carboxylic functional group. If your alkaloids contains carboxylic group, it will produce effervescence upon the addition of aqueous sodium bicarbonate solution and will get dissolved in the aqueous solution of sodium bicarbonate. So this is a confirmatory test for the presence of carboxylic functional group. For the quantitative estimation of carboxylic group, titrate the given unknown sample of alkaloid with bismuth hydroxide solution by using phenolphthalein indicator. It will give you the quantity of the carboxylic functional group present in your alkaloid sample. Fluorescence test is a highly sensitive test for the detection of carboxylic acids in your alkaloid sample. This test is given by the dicarboxylic acid alkaloids only, which on heating, first of all you have to heat the alkaloid, which on heating will produce an anhydride. This anhydride will react with the resorcinol in the presence of concentrated sulfuric acid, and a fluorescent dye formation will indicate the presence of dicarboxylic acid. Here I have given the example of a anhydride formed from a dicarboxylic acid, and it is reacting with resorcinol in the presence of sulfuric acid, and a fluorescent is formed. Since fluorescent is a fluorescent molecule, so the high detection limits of the fluorescence make this test very sensitive for the detection of carboxylic acids. Oxo, also called the carbonyl group, may be present in alkaloids in many forms, such as it may be present in the form of an aldehyde, it may be present in the form of ketone or an amide. Different chemical conversions or reactions that can be used for the detection of carbonyl groups in the alkaloids include the reaction of amine, primary amine with the alkaloid having the carbonyl functional group. The reaction of the carbonyl with the primary amine will produce an imine. Similarly, the reaction of carbonyl with the functional group with the hydrazine will produce the hydrazone, and the reaction of hydroxylamine with the carbonyl functional group of the alkaloid will produce the oxime. Semicarbazoid upon reacting with the carbonyl group of the alkaloid will produce the semicarbazole, and similarly the aryl hydrazine upon reacting with the carbonyl functional group of the alkaloid will produce the aryl hydrazone. These chemical conversions can be used for the establishment of the presence or the absence of the carbonyl functional group in alkaloids. Alkaloids from the plant sample or animal samples are separated through the thin layer chromatography. Once they are separated on the thin layer chromatogram, their detection on the thin layer chromatogram is necessary. For this purpose, the thin layer chromatogram is sprayed with a reagent that that react with the alkaloid and give a specific color. These reagents can be used for the detection of alkaloids on the chromatogram, on the thin layer chromatogram. The one is called the Adam-Cavies reagent. It consists of a mixture of formaldehyde and hydrochloric acid. You may also use the Morphel's reagent. It is a mixture of formaldehyde and concentrated sulfuric acid. Mackel's and Mill reagent can also be used for the detection of alkaloids on thin layer chromatogram. It is a mixture of orthophthaldehyde and hydrochloric acid. 2,4-DMP can be used to qualitatively detect the aldehyde and keto functional groups. A positive test is the formation of a yellow, orange, or red precipitate, aromatic carbonyls from red precipitate, whereas the aliphatic give yellow color. A general reaction between the 2,4-DMP and a ketone is shown in this slide. The next question is how to differentiate between an aldehyde and a keto group. The answer is the Tollens and the Fillings test. Tollens reagent is a chemical reagent used to detect the presence of aldehyde functional groups along with some alpha hydroxy ketone that can tautomerize into aldehyde. So it exclusively determines the aldehyde, although it is detecting some alpha hydroxy ketones which are present in the aldehyde tautomeric form. The Tollens reagent was discovered by a German chemist Bernhard Tollens. A positive test with Tollens reagent is indicated by the precipitation of elemental silver, also called the silver mirror test, often producing a characteristic silver mirror on the inner surfaces of the reaction vessel, such as the test tube. The Tollens reagent consists of a solution of silver nitrate, ammonia, and sodium hydroxide. Sodium hydroxide is added to maintain its basic pH. So if your alkaloid contains an aldehyde functional group, it upon reacting with the Tollens reagent will produce a silver mirror. So a silver mirror will be produced on the sides of the test tube. Filling solution is a chemical reagent used to differentiate between water-soluble carbohydrate and ketone functional group, and is a test for reducing sugars and non-reducing sugars supplementary to the Tollens reagent test. The test was developed by German chemist Hermann von Filling in 1849. The solution cannot differentiate between benzaldehyde and acetone. Filling solution is prepared by combining two separate solutions known as filling solution A and filling solution B. Filling solution A is aqueous solution of copper sulfate which is deep blue in color. Filling solution B is a colorless solution of aqueous potassium sodium tartrate, also known as the Rochelle salt. This Rochelle salt is made alkaline with strong alkali, commonly with sodium hydroxide. Typically the levorotatory tartrate salts are used. The copper 2 complex in filling solution is an oxidizing agent and the active reagent in the test. The deep blue active ingredient in the filling solution is base tartrate complex of copper 2. The tartrate tetraanions serve as bidentate alkoxide ligands. How we can prepare the fillings reagent? Let's learn it. A fillings reagent is a mixture of copper sulfate solution, also known as the solution A, and the alkaline sodium potassium tartrate solution, also known as the solution B. The solution A and B are prepared as according to the my described recipe. For the solution A, you have to dissolve 34.65 grams of copper sulfate in 400 ml of distilled water and make the final volume 500 milliliter with distilled water. For the preparation of filling solution B or the alkyl sodium potassium tartrate solution, you have to dissolve 125 gram of potassium hydroxide and 173 gram of sodium potassium tartrate, also called as the Ruchel salt, in 400 ml of the distilled water and make the final volume 500 ml with the distilled water. Both solution A and B are separately prepared and stored separately under the dark conditions. Whenever required, filling reagent is prepared by mixing equal parts of the solution A and solution B, always freshly.